Hi, so my name is Jianneng, and I work at Workday. This talk is about building a data prep tool on top of Spark. First things first, anything I say may or may not be true and cannot be held against me, so pick your battles wisely. That being out of the way, I am at Workday. Workday is a big company though, so more specifically, I work on a product called Workday Prism Analytics. What is Workday Prism Analytics? Workday is a big company again, and we are a cloud solution for companies' HR data and financial data. That's very important data of a company. But when you have a lot of data, naturally you want to make sense out of them. You want to perform analytics on top of the data. So the goal of Prism is to take data you have in Workday, combine it with data outside Workday, and make rainbows out of them. More concretely, we take the data that's inside Workday, the financial and human capital management data, and also take the operational data from a business. For example, data from your CRM, your Salesforce, blend them inside Workday. For example, by applying transformations, doing data cleaning operations, applying security, and then publish them into data sources to eventually be able to derive insight out of them. These insights could be reporting, could be reports, scorecards, it could be even visualization that analysts would do to eventually perform getting dashboards and charts to show to the executives. And for this talk specifically, I'll be focusing on the data preparation side of it. Before we're going to dive into the more details, I want to give you an example of what Prism could be possibly used for. What does it really mean when you say data inside Workday and data outside Workday? So for example, we have one customer use case that takes the human capital management data, their worker data from their organization, do some data munging to get the top performance of the workers, and then also take from outside Workday the stock vesting schedule of these workers to basically understand whether their stocks are kind of vesting soon so that they should be awarded more options before they will consider leaving the company before their shares have vested up. And another thing to kind of note here is that we are really a solution that allows other people to build data pipelines on top of. And this is kind of different from most other talks you might have seen where organizations have their own data solutions and they will write custom Flink jobs or Spark jobs to do these data munging queries. For us, we build a UI that allows other people to visually express what they want to do with their pipelines. So at the end of this talk, I want you to all go away with 3 points in your head. 1, there are many interesting challenges inside data prep. 2, Spark is a pretty good engine for these challenges. And 3, Workday is hiring and we would love for you to join us. Okay, so 3 minutes in and finally I can get into some technical details. What is data prep that I've been keep on telling about? Well, if you know ETL from the traditional business intelligence world, it's very similar to that, but with a modern twist. So traditionally, ETL is a process by which business use to extract raw data and then apply transformations on top of them, and then load them into a database for faster querying. But traditionally, this is very technical. It involves data engineering, it involves complex SQL queries, and it's typically done across 2 different organizations. You have the data analysts that want to answer specific questions, so they tell the database admin to run some queries. And finally, the database admin will get the results back, put them into a place where the data analyst can access. And then the kind of iteration process is very, very long. But as data gets democratized, you want to be able to have even non-technical people access the same amount of capabilities. And that's what data prep is really about. So it should be intuitive, it should be easy to use, and it should be also flexible enough to handle all the different possible work cases. And another thing that traditional ETL might not provide you is that traditional ETL are already batch jobs where you run the SQL query and finally you get results back. And again, the time it takes for this is very long. And we want to reduce the iteration time. So as people start to build their pipelines, they can quickly see their results and have a feedback loop. So this is what data prep looks like in Prism. we have kind of defined every single transformation you might want to think about. So a join, a filter, a group by, a union, into this concept called a transform stage. And the list of transform stages is kind of on the left. It's showing the primary pipeline of the pipelines and all the secondary pipelines that kind of join into the primary pipeline. They're kind of hidden away so that it's easy for you to see a progression of the stages. On the right side, you can choose the number of samples that you want to sample. And finally, we'll show you the examples and statistics on top of these samples. And then if you, for example, click on editing for one of the stages, you have the option of editing the different things you can do. For example, in this case, this is a filter, so you can add additional filters, you can change the existing filters, you can do all the things that you can want to do with the filter. And on the right side, this data that you see is powered by Spark. And that's what we mean by building a tool on top of Spark. We handle kind of the logical compilation, and we kind of put the workhorse as the Spark engine. So why Spark? Like I mentioned before, Spark, data prep needs to be both interactive and needs to be batch. It needs to be able to operate on a sample of the data and also be able to scalable. And that's something Spark is good at. It's able to return quickly when the result is small, and it's also able to crunch very, very large numbers. Spark has a very modular design. Every single part of Spark, Spark ML, or I guess, yeah, Spark ML, and Spark Streaming, their optimizer, their core package, they're all separated into their own modules. And if we don't need to use a part of them, then we don't have to use it. Spark is very extensible. We can take any operator and extend it, or we can add additional operators, and also, in addition, adding changes to their optimizer so that we can get what we want to do. And finally, it's a very active community. There are many commits going in, and releases are quite frequent. And honestly, having this support from the community is very important. So how do we really use Spark then? So like I mentioned again, there's two types of workloads. One is interactive and one is batch. And we kind of launched two different workloads, two different applications for each one of them. For the interactive side of it, we launch a always-on, always-running application that will basically stay on forever and be able to service requests live as they come in. And the results, because they're pretty small, are typically just returned inside memory. And then for batch jobs, we would execute this over the entire data set and then write the results to HDFS. And this is kind of like the load process where we write the results in an efficient format that is easy for query so that when downstream queries come in, we can quickly serve the requests. Going in a little more into detail, how do we really compile this into something that Spark can understand? If you've ever worked with kind of logical plans, something pretty simple could be, say, we have imports on the left, we have a join, and we have a filter. So it's kind of just nested structure of logical plans that can be translated into something that machine can understand. But this is an interactive interface, right? If we simply just execute everything for workers again could be terabytes in size, or maybe not workers, but it could be journal lines or something else that could be very, very large. And therefore, we don't want to execute over the entire thing. Therefore, we have to add some additional limits in this plan so that we can keep the results small and also hopefully relevant. So in this case, we would apply sample operator on top of every single scan. In this case, the scans are workers. And in this case, we scan 1,000 rows out of however many rows that the data set might have. And finally, because we want to, the user really just asked for 1,000 rows, so there's really no point returning more rows than asked. So in this case, we would return also 1,000 rows by limiting the number of results to be 1,000. Okay, so this sounds pretty straightforward, right? What could possibly go wrong? Well, let me show you what could possibly go wrong. There are many things that could be traps that you might not realize when you're building a system like this, because every time user is involved as an interaction, users might be doing something you don't expect. Or the data in the real world is very nasty. It's usually not very clean. It's very it's not as structured as everyone would have liked. And for the rest of this talk, basically, I will be focusing on some specific challenges that we kind of faced. And I'll be focusing on joins, because that's sometimes the most painful part of these. One challenge, is the results could be too large. And for an interactive query, we really want the results to return quickly. But when you have a very large amount of data, it's kind of hard to crunch out these numbers very quickly. So we want to keep the queries running fast. And for queries to run fast, we want to have the data sample to be small and relevant. So this is, again, the same plan that I showed you earlier. And it shows that you're joining two data set of workers. You're doing a self-join. This is a pretty contrived example. If the join key is very unique, like user ID, then we're OK, because likely you'll just get at most 1,000 results back. But what if you're joining on something that's very generic, like gender? And if it just happened that your workers' data set is partitioned such that all the males are on top, then the first 1,000 records might be all of the same gender. And in this case, you get a cross-join. And the results would be 1 million. And then, sure, we filter it in the end so that we only get 1,000 back. But having 1 million intermediate results is really excessive. And in this case, we're just really sampling 1,000 rows. What if we're sampling 10,000 rows? Then we'll have 100 million results, and that's really a lot. Sometimes it might not even fit in memory. And that's going to cause a lot of performance problems and also CPU overhead. So what do? We would place intermediate limits also on intermediate joins. And empirically, 100,000 rows is kind of the limit. It's a pretty good balance between the performance and also the result size. In the worst case, it can probably return in seconds and not minutes, which is pretty unacceptable. So that's one side of the spectrum. The other side of the spectrum, which is more common, is what if you have no join results? Because really, you're kind of at the mercy of your sampling algorithm, right? You have data that's sitting somewhere, and depending on how you sample the data, you could be basically getting no results. Let's say the most naive case, you're only sampling the first, 500 kilobytes of data. It might just be the case that the data does not have keys that match. In this case, we have a contrived video views table and a users table. We want to join on user ID. And these are all the possible joins. But let's say we're only sampling 2 rows. Then you see that the first 2 user IDs are not good enough for us to get a result. And getting a result is especially important because we want the user to have a feedback as they're building their pipelines. So what do? The solution we're using to tackle this is something called correlated sampling. It's a known technique from the database world where you feed every single join key into a hash function. And given the output of this hash function, only keep this row if this hash function result is less than a certain threshold. That effectively basically reduces the space of possible key values inside your data set. And therefore, you have a smaller search space and hopefully a larger possibility for getting results. Practically, the way we apply it is we would, again, hash the result and then also scan more data. Because we're only in the end keeping k rows, but that doesn't mean we only have to scan k rows. In this case, we scan to 10 times the number of rows asked, and we maintain only the number of records as necessary. And the eviction kind of policy in this case is we're keeping the one with the smallest hash values. So how that works in this case is, let's say the hash function is just very simple identity function. Then for only k rows, we're really sampling 20 rows. So we're basically sampling everything on the screen. And if you look at all the user IDs, we're just keeping the smallest ones. So in this case, we'll have 1 and 3 on the left and 1 and 2 on the right. And from there, we're able to get a join. That's a pretty simple case. It gets a little more complicated than that. As an extension of this problem, sometimes you have many, many repeated keys. Right? This is also a pretty common problem. You can have keys that are just repeated because the records just happen to be next to each other. let's say you have, for example, a clickstream data, you might have the same user ID doing multiple operations continuously. So it's something that's very common in the real world. And if you're using the naive solution where you're only keeping the smallest hash values, then in this case, you're only keeping all the 2s on the left side, and therefore not be able to get any result on the right side. The way to tackle this is to use this concept of buckets. In short, every single key is its own bucket. And this bucket, we can specify a bucket size for, let's say 2. If the number of sample rows you want to keep is not reached, then you can keep on growing the number of entries inside this bucket beyond B. But if you're reaching a case where the number of rows you want to keep is reached, and there's a new key coming in, you want to start evicting the buckets with the number of values more than B. This way, you are basically limiting the maximum number of entries you can keep for one bucket, and therefore hopefully have more cardinality. So in this case, let's say B equals to 2, and again, hash function is the same as before as the identity function, and we want to sample 3 rows. We take the first 3 rows, and now we have reached k equals to 3. Now for every single new entry here, we want to decide whether we want to keep here or not keep it. In the first one here, the B is already reached, and therefore we're just going to skip it. Second one is the same, third one is also the same. And then we reach the 3. 3 is a new bucket. And because we already have a bucket for the value equals to 2 with the value more than we want to keep. Therefore, this should be kept, and one entry from the bucket for B, for a bucket for 2 should be evicted. So then after sampling and after eviction, this is what we end up with. And now we have something that both sides has, and we can finally get some results back. There are many other challenges in data prep that I did not touch. I was very ambitious when I wrote my abstract, and but the reality is I can only fit so much within a 20-minute talk. But if you are interested in any of these, what these bullets could mean, I'm really happy to stay around and talk to you about it. In addition, we'll have more members from Prism actually in the audience today, so we can have a talk after. That's the end of it. Thank you. If you have any questions, I can take them now. Wow, I explained everything. Oh, okay.
I wasn't clear. Why is it running on Spark, or is it really you're showing a sample here and then you want to run it on large scale?
So for data prep, there are 2 types of workloads you want to run. So the question is, how does Spark come to play here, right? If it's really a small sample, why do we want to use Spark? You have 2 things here. One is interactive part of it, where users want to see results as they go on. But ultimately, what the user wants is to get results in the overall data. And why Spark is useful here is you can have the same plan for both the interactive part and the batch part. The only difference is for the interactive part, you would add the additional operators into the plan to do sampling and to do limits. And that's very powerful because you're using the same engine for both workloads, and because it can. All right, thank you very much.